right, page 290 in your textbooks. You answered questions 3, 5, 6, 7, 10, 11, 13, and 15 for homework last night. A little bit of a longer assignment. No math, though, for a change. Question number 3, what is reflectance, Michael?
Reflectance is the ratio of total reflected light to an object surface. Wait. Total to reflected light of an object surface.
He started off on a good note, just kind of didn't finish his ratio. Audrey?
Reflectance is the ratio of the reflected light to the total light falling on a surface.
There we go. Ratio of reflected light to total light that falls on the surface. I think you kind of had that, but left off a couple of keywords that made it make a little bit more sense. Usually expressed as a percent, so usually we write it as a percentage of reflected light. Number 5, why can you not see yourself in a piece of white paper? Kendall?
You can't see yourself in a piece of white paper because it reflects most of the incident light.
But shouldn't that mean you see, like, after all, if it reflects most of the light that hits it, shouldn't I see myself? Like, I kind of see my gold tie right now a little bit. I even see the blue stripes. See, look. You see the gold and the blue stripes? I mean, you can see, but why can't you see yourself then? If I can see my tie, if I put it close enough, right? I mean, it's reflecting the light, right? Why can't I see myself in a piece of white paper? Michael, what did you put?
The paper has the diffusion property, not specular.
Right, because the paper is uneven, it's a rough surface, it reflects with diffuse reflection, right, where the light rays are scattered all over. So the light is reflected just like it would be from a mirror, at least in the sense that as much light as would be reflected from a mirror is reflected, but instead of being reflected back to you, it's reflected everywhere else. That's why. Number 6, state the 2 laws of reflection. Back to Kendall.
The 2 laws of reflection are the angle of incidence is equal to the angle of reflection, and the incident ray, the normal, and the reflected ray lie in the same line.
Good, and we're going to be playing around with that here in just a little bit. Let's see, number 7. What's the difference between a real and a virtual image, Audrey?
A real image is formed by light actually passing through a point. A virtual image has no light rays that pass through an image.
Yeah, I'll give that to you. Good. A real image, light rays really reflect off of a mirror and they really converge to form an image. Virtual image, the light rays seem to go through the mirror and converge to form an image behind the mirror. That's impossible. Light can't go, well, it's a two-way mirror, but the light isn't going through the mirror. The image isn't back there, but it seems like it is. So a real image is formed in front of a mirror by light rays that really reflect off. Virtual images seem to be formed behind the mirror. Number 10, distinguish between concave and convex mirrors, getting into what we're going to talk about tomorrow. Michael.
Concave mirrors form a depression and seem to flip the image, and convex mirrors form a bulge.
Okay, you gave me a little more detail than I even needed necessarily, but that's not wrong. Good. Concave mirrors cave in, and convex mirrors bulge out. Now, there's a better definition, I suppose, but for now we'll take that. Let's see, number 11. What's the difference between the vertex and the center of curvature? Kendall?
A vertex is the center of the mirror surface, while the center of curvature is the center of the sphere that contains the mirror surface.
Good. What we're going to look at tomorrow are spherical mirrors, and I'll say it this way. Repetition's key to learning, so I'll say it again this way in the next lesson. But if you picture a great big ball of mirror, it's a ball, it's a mirror. If you were to find the center of the sphere, the center of the ball, that's the center of curvature, right? Where all the radii to any point along the ball is the same. But if you actually chop the mirror without it shattering, okay, just slice the mirror, if you were to set the mirror down on its little bowl-shaped self, the center that it sits on is the vertex. By the way then, going back to taking that ball of mirror analogy, Michael, I would say you have a big ball of mirror. If the outside of the ball is reflective, it's convex. Chop. The outside is reflective, that's convex. If it's not until you chop it open, like a geode, right? If you chop it open and then the inside has the mirror surface, that's concave. But practically it caves in versus it bulges out. It's a really good way to think of it as well. Let's see, numero 13. What did I say? How is focal length of a spherical mirror related to the radius of curvature, Audrey?
The focal length of a spherical mirror equals the radius of equals 1/2 the radius of curvature.
There we go. I was about to say, how did you miss that? It's half the radius of curvature. Very good. And number 15, what are the three principal rays? Michael?
The three principal rays are the central ray, the parallel ray, and the focal ray.
Very good. And we'll be looking at ray diagrams in our next lesson as well. Any questions on the homework? All right, set that aside if you would. Keep your books open here though, because we're going to be looking across the page at page 291 here in just a moment. Quick review of some terms yesterday. Remember, we said that the study of light is called, class? Optics. And the study of light in the sense that we assume light has an infinite number of infinitely thin parallel rays is specifically referred to as geometric optics. We're going to look at light as being composed of rays, these straight line beams. Now, does light actually travel as straight line beams? Well, not necessarily, but since we're familiar with laser beams, and we'll be looking again at that today, it's a good way to think of light, and it'll help us to discover some things about light. If we go on to chapter 21, which is actually one of the chapters we're going to be jumping over very quickly, we'll look at wave optics, where we look at, okay, now let's look at the wave property. Remember we looked at that single slit, double slit interference patterns? That's in chapter 21, rainbow dispersion of light. Chapter 21, that's all because light behaves as a wave as well. So that's stuff that we're going to touch on briefly and then skip past it, kind of like we did to chapter 15. There's not a lot of math in there, and it's stuff that, while it's interesting, could be learned kind of on your own, frankly. We said that when light strikes a surface, a few different things could happen. As light hits a surface, the light class could be absorbed by the surface. Not all of it, maybe all of it. Well, okay, frankly, no, never all of it, but a lot of it could be absorbed. Light could also be reflected off. Not all of it, but a lot of it could be. Light could also be transmitted through it. And finally, light could also be scattered. If it's translucent, the light will be scattered through. If it's transparent, it'll be transmitted through. Anything else, remember we said it'll either be reflected or absorbed. We just looked at the video. Those on YouTube could have seen it yesterday in the description of yesterday's lessons video. But looked at those videos of the Vanta Black and how, you took ordinary matte black paint. If you were to, I don't know, maybe you're really morbid or you want to paint your bedroom black. I don't feel like that would be good. But if you did, just really like it. They showed, a normal white light, flashlight, maybe it's from a cell phone even, shining on that matte black paint. Okay, you see a little bit of light reflected off. They showed it over the black paint that they use in at NASA for the nose cone of the space module, things like that. Okay, well, that's even darker, a little less light reflected. They showed it on the Vanta Black, and you couldn't tell anything. You see the light on either side of it, but you didn't see any light reflected off. Laser beam didn't even reflect off. So with that, we said that there's very little light that reflects. Most of the light is absorbed. If we were to take that percentage of reflected light to total light, we call that class? Reflectance. And they said with Vanta Black, the reflectance is around like 1.6% reflectance. Very, very low reflectance. There were a couple pictures on Twitter as I was looking at this. I didn't feel like posting those, but a couple pictures on Twitter of somebody who had a disc that had the Vanta Black on it. And it really looked like someone had just gone through with Photoshop and put a black circle on there. No light reflected off at all. You wouldn't have thought it was actual photo, but it was. Whereas stuff like white reflects a great deal of light that hits it, right? We had talked earlier about high reflectance is going to keep you cooler in the summertime. Today it's actually cold again. Why? We don't know. It's Georgia. But so today maybe you want to be out in the sun. I took a walk yesterday afternoon. I went to the chiropractor and I had a bit of a wait for my visit. So I just took a walk around the complex there. And I decided, as windy as it was and as cool as it was, I think I wanted to be out in the sun today. So I wanted that energy to be absorbed. We said there's two types of reflection. Something that is very smooth. Maybe the surface of the cell phone. I don't know if you ever used that, but I can. Hi, Kendall. Hi, Audrey. Ah! Just kidding. But it's a nice smooth surface, right? This isn't a mirror, but it's still a smooth surface. So class, we get what type of reflection? Specular reflection, right? And it's because the surface is nice and smooth, light rays that come in parallel, class, reflect off parallel. They stay together. So that the light rays coming from Michael to the phone stay all together, so I see Michael. Whereas here, Hey, that's better. Light rays come from Michael, but they don't all come to my eye. Some of them go over there, some of them over here, and so we don't get a clear image. This is called, class, diffuse reflection. What is it, class? Diffuse reflection. The reason is that the paper is somewhat rough or uneven. It's not perfectly smooth where light rays stay parallel. We already said the two laws of reflection in the homework. First of all, class, the angle of incidence equals the angle of reflection. Both of these are measured with respect to the normal. That goes back to something we covered in chapter 15. And both the incident angle or incident ray, if we want to think of it that way, the reflected ray and the normal all have to lie in the same plane. What if it's striking an uneven surface? What about like this, the curve right here on the water bottle, or the curves here on the water bottle? When light hits that, how do we figure a normal and an angle and all of that? What did we say we had to do, Audrey? We've got this, this curved surface, and a light ray comes in and hits it.
It's perpendicular to the tangent line.
Good. We would have to figure a tangent line at that point, and then the normal would be perpendicular to the tangent, so that's how we measure the angle of incidence, right? And so the angle of reflection, of course, would go off at the same angle then. I believe that takes care of everything we covered. Just a little bit of math with this. And so page 291, you're already there. Problem number 1. Go ahead and read that problem for us, if you would, Michael.
While you are looking at an image of your feet in a plain mirror, you see a scratch in the glass. What is the approximate height of the scratch from the floor, assuming your eyes are 1.75 meters above your feet?
All right, so let's draw a little picture. You can do this on your paper as I do this here. You are standing there, so draw you. I'll draw Michael. Feet. Okay, Michael. All right. Just kidding. He's not actually covering his eyes because otherwise he wouldn't be able to see. Anyway, so there's Michael. I'm going to miss you, Michael. There's Michael. He's got short arms. And he looks in a mirror. Mirror, mirror on the wall. Who is big and who is tall? All right, so anyway, he looks at the mirror. Now, obviously, he doesn't have to look down to floor level to see his feet, correct? In fact, he has to look where to see his feet? Here's feet, here's eye. Where would he have to look to see his feet in the reflection?
At the mirror.
Where at the mirror, though, right? Would he have to look right here at the mirror? Would that help him to see it? No.
Is the mirror vertical?
Yeah, mirror, assuming the mirror is vertical. Yeah, that's true. Let's establish it's a wall mirror that's vertical. Good point.
45 degrees.
He'd have to look at a 40, you're giving it more detail than I'm looking for, halfway down, right? 45-degree angle, I guess, is what, well, depending on where if the mirror's really close, it'd be a steeper angle, wouldn't it? He'd have to look halfway down, though, wouldn't he? Because whatever this angle of incidence is going to be the angle of reflection, so it's really just halfway to the feet. Does that make sense? So here's the thing, ladies. Either of you have a full-length mirror in your bedroom by any chance, maybe hanging over a door or on the wall or something. There's a full-length mirror in the girls' bathroom. I was in there several years ago. I don't know if you would remember this. They used to have over the sink, they had a little bitty short mirror, and they had rectangle mirrors, and they were different. And the problem is everybody could see them because when you come up the stairs, as soon as that door opens, you get a straight shot look at the girls' sinks. It bugged the fire out of me. So I changed them out one year. I bought new mirrors, and I hung them up, and I changed out the soap dispensers and the paper towel dispensers because everything was old and jankety, as your cousin Daisy would say. Shout out to Daisy. And anyway, I turned around and I noticed the full-length mirror. And the full-length mirror is like a foot off the ground. Whoever hung it didn't realize this. You don't have to have it go all the way to the ground. You can see your feet at the halfway point. So even if a kid would literally have to be only 2 feet tall to need the mirror to be a foot off the ground. Assuming the kids up here are at least 4 feet tall, you could have the base of the mirror how high off the ground? 2 feet off, right? So that way you're seeing halfway there, right? So it says that his eyes, going back to the problem here, that the person looking in the mirror, he's got a smile on his face, he's got high self-esteem, right? And And because he recognizes he's made in the image of God. Of course, there's no reason for low self-esteem. And his eyes, it says, are 1.75 meters above his feet. Okay, then how high off the ground will he be looking if, as he sees his feet, he sees a scratch in the mirror? As he's seeing his feet, it's like, oh, there's a scratch in the mirror. Okay, then where is the scratch in relation to the ground? Pretty easy math. 0.875 meters. Well, I guess technically above his feet. I guess the feet are technically not like at the ground. They're like, half an inch to an inch above the ground. But 0.875 meters above the feet, right? That's where the scratch has to be. The nice thing with a plane mirror is the math basically just involves halves, because the angle of incidence equals the angle of reflection. So just cut whatever numbers you want in half. Make sense? So really, truly, then, for him, he could actually hang the mirror 7/8 of a meter off the ground. He could still see his feet, right? This kind of builds on the next one. Number 3, go ahead and read this one for us, if you would, Kendall.
850 centimeter lady is wearing a bonnet that rises 25 centimeters above her head. Assume her eyes are 11 centimeters below the top of her head. To see her entire reflection, bonnet and all, what is the minimum length of the mirror? How high off the ground must the mirror be?
All right, so this lady is right about 5 feet tall. 150 centimeters is right about 5 feet. So, sorry. So we've got this 150 centimeter lady. But 150 centimeter lady is wearing a bonnet. Like, those old style bonnets. Kind of looks like an afro the way I draw it. But she's got a bonnet on, and it says the bonnet rises an additional 25 centimeters above her head. Does that make sense? So total height of woman, 175 centimeters. So Michael height, right? She's almost 6 feet. Well, actually, Michael's taller than that. But this would be almost 6 feet tall. We're closing in on that. But her eyes are not at the top of her head. Where are her eyes, according to the problem?
11 centimeters.
11 centimeters down. So 11 centimeters is about the width of a man's hand. And from the top of the head down, probably pretty close. So her eyes come down 11 centimeters. Does that make sense? So from eyes to top of bonnet, what is the total height from her eyes to the top of the bonnet, class? There's a neat 36 centimeters, right? And then from eyes to floor, where her feet are, how many centimeters? 139 centimeters. Does that make sense? Okay, so theoretically, we're on a tight budget. We're going to get the mirror cut to exact specifications. How high off the floor is the bottom of the mirror going to need to be? How high off the floor is the bottom of the mirror going to have to be? We need to start at 69.5 centimeters off the ground. Does that make sense? Now that's bare minimum. That means right at the very base of the mirror we're seeing her feet. Okay? But bare minimum. All right? Now, her total height, including bonnet, goes up to 175 centimeters. But we don't need the top of the mirror to go all the way up to 175. We could come down how far from the top of the bonnet? 18 centimeters. Remember, from top of bonnet to eyes is 36. Everything with a plane mirror revolves around halves. So if we come down just 18 centimeters from the top of the bonnet, we'll have that now as she looks in the mirror, she's seeing the top of the bonnet right at the very top edge of the mirror. So, remember, total height, 175, but we're able to come down 18. So how high to the top of the mirror? If we come down 18 centimeters.
157.
We come down to 157 centimeters to the top of the mirror. So we need to hang it so the top of the mirror is right at 157 centimeters. I guess she's not wearing shoes. Maybe this is wearing shoes. Anyway, the bottom of the mirror right to 69.5. So, how big of a mirror do we need? We don't need a 4-foot full-length mirror for this woman. We only need a mirror that is 87.5 centimeter mirror, hung exactly 69.5 centimeters off the ground. Now, there'd be a really easy way to get 87.5 centimeter mirror. If all it had asked was, how big does the mirror have to be? There's a really easy way to get that. Just take her total height, cut it in half. So if Audrey, you're how tall?
5'4".
5'4", okay, and the biggest heels you will wear comfortably. So if you're going all out with the high heels, how high are these heels of yours if you're wearing high heels?
Probably 2 inches.
So you're like, I don't want the 3/4, certainly not the 6-inch stilettos that just look scary. 2 inches is a good comfortable number for me. All right, so 5'6" would be your probably the maximum height you would ever be. Okay, so then, you ever envision yourself like doing like a pompadour hair, where it stands all up like on the Coke bottle thing? Would you want to be able to see that? Let's just suppose she loves the Coke bottle hair. You know what I'm talking about? You pull the hair up, stick a Coke bottle inside, and okay. So let's just suppose she wants to be able to do Coke bottle hair. Coke bottle's what, about 8 more inches? Let's say that takes her up to, she's wearing high heels at the same time she's got the Coke bottle hair, so that takes her up to 6'2". All right? If that is the absolute tallest Audrey's ever going to be, is 6'2", including all those extra accoutrements, how big of a mirror does she need? Bare minimum. To see herself completely. 3'1", 3 foot 1 inch, or 37 inches, right? Now, to be fair, do you want your feet to be right at the bottom edge, right as the top of the hair is at the very top edge? Probably not. So that's where a 4-foot mirror might be nice, right? You get a little wiggle room there. You don't have to be quite as careful where you hang it. But in theory, yeah, you can get by with less as long as you hang it strategically. Right? Halfway up to your eyes would be where the bottom would have to be, or if it's a bigger mirror, it can go a little lower than that, but it doesn't actually have to be at ground level. Now here's the struggle that I had. Not that I ever go in the girls' bathroom to see how I look, but while I was in there, I turn around, look at the full-length mirror, and there's the mirror. Well, I could see my feet right here. I don't need all this down here, but I can't see the top of my head, because it doesn't extend above the top of my head, right? So I'm like, whoever hung this clearly did not hang this for the benefit of Mrs. Kauser while she was teaching here. Because I think she's taller than I am.
She's 6'1".
If I say she's 6'1", I'm 5'11", with shoes maybe I touch 6 feet, and she's even taller than I am. Like, that mirror had to drive her nuts. So anyway, yeah, you want to make sure the top of the mirror extends above you just a little bit, and the bottom of the mirror doesn't actually have to go down that low. Just halfway down. Questions on the math related to plane mirrors? All right. Well, there is no homework for this lesson then, and we'll talk more about spherical mirrors in our next lesson. We're going to play around with lasers and mirrors from here